Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC1004. We are now in lecture 7. So this is your attendance. Please scan the QR code and make sure that you key in with your new matrix number. So we are now discussing on the third law of thermodynamics. And this third law of thermodynamics is very much tied to the absolute zero. And when we talk about absolute zero, that is the lowest point on the Kelvin scale, and 0 Kelvin is possibly the lowest temperature in the universe. And this corresponds to minus 273 degrees Celsius. Now really it's hard to imagine how cold this temperature is, and in order to do that, in trying to imagine that, I thought, why don't we just look at the coldest inhabited place on Earth, and probably by looking at some pictures and reading about the life in the coldest place on Earth, we can imagine how cold this absolute zero is. At least we're trying. So if you read about Oymyakon, which is a town in Russia, it is one of the candidates for the northern pole of coal. Now the ground there is permanently frozen because winter lasts for 9 months there. And this town is located in the Russian Republic of Yakutia in Siberia on a plateau 750 meters above sea level. And so they have mountain ranges that prevent this cold air to actually escape. Now daily temperature is below is minus 50 degrees Celsius, or even much lower than that. And the lowest temperature recorded was minus 71.2 degrees Celsius. No, that's really hard to imagine. And so what is it like to be in Oymyakon? Now here are two links. One are pictures and one is a video. I will try to click on this. I've tried to do this while recording. It may not work. If it doesn't work, I'm just going to show you the pictures. If this doesn't work either, so you can do that independently just by try to go to this link and actually look at those pictures and this video yourself. I'm going to try it now and see whether that works. Oh good, it works. So this is actually boiling water being thrown into the air and it becomes ice. This is your transport, one of your transport to go to the university, I guess. Not so bad. So here it says minus 47, it can go, about minus 50. Your eyeglasses will be foggy because of the weather. It's just really like frozen, isn't it? We're not going to be happy about this, but I'm sure they work some way out in terms of how they actually use their mobile phone. And guess what? This is like the Alibaba story, the restaurant. So they have to be meat eaters or fish because they can't grow anything due to the frozen ground. So they only eat meat and fish. So we are not complaining because our city is not cold. So let's look whether we can actually get access to these pictures. so that's quite slow, so we're going to skip that, and so you can actually look at this yourself. Okay, so anyways, let's go to the rest of the lecture. Oops. So if you've been to Omayacon, you will definitely want to post in your Instagram or Facebook to show the certificate that you've been there. And so this is something that you can be proud of, that you have been to this pole of coal in Omayacon, and it says here that the lowest temperature recorded is as such. And so yeah, so this is something Instagrammable or Facebookable that people would like to put in social media. So now, if you think that is cool, okay, that this is your OOTD to class or to the shopping mall or outside, even doing normal activities, okay, if you think that this is cold, the absolute zero in thermodynamics is even colder than that in Omayacon. So it is perhaps the lowest temperature in the universe, as I've mentioned, and so it is really, really much colder than this frozen ground, frozen environment there. So in actuality, no system can have a temperature of 0 Kelvin, because there's always movement of that's going on. Heat can never spontaneously move from colder body to hotter body. So as a system approaches absolute zero, there's always this the drawing of energy from whatever systems nearby, and when that happens, that absolute zero is quite impossible to achieve. But if you want to visualize, but this third law of thermodynamics talks about this absolute zero, so in order for us to visualize how that is, you can think of something as simple as water. So water vapor, as in this gaseous state, is molecules that moves around very freely, has very high temperature, very high entropy, and when it cools down, it becomes liquid. And this liquid water molecule, it can still move, but it's not as freely as in when it was in the state of water vapor. So it has lost some entropy when it becomes water. So when the water cools further, it becomes solid ice, and then its molecules can no longer move as freely as before. It vibrates though within the ice crystal, so the entropy becomes much lower. So as the temperature gets even colder, closer to absolute zero, so even the vibration stops. So if the solid water were to reach absolute zero, there's no motion at all, absolutely, no molecular motion, absolutely zero. So then there will have no entropy at all. So this is how we imagine this, absolute zero is when there is no molecular motion, no entropy at all. So we can imagine that, for this, the application of this, this third law of thermodynamics is usually for ultra low sub-zero temperature in chemistry and physics experiments. So, but the idea is that, okay, to imagine how motions are, how things are when it is actually in that state. But of course, in terms of this application, it's not used directly as much as you have in the first and second law of thermodynamics. So the third law of thermodynamics In other words, okay, the entropy of perfect crystal at absolute zero is exactly equal to 0. So at 0 Kelvin, the system is in a state with minimum energy. So the perfect crystal has only one state with 0 energy. So as temperature approaches 0 Kelvin, so the entropy becomes 0. And when you learn statistical thermodynamics, you're going to learn that in your third year, I think, third or second year. Okay, so entropy is related to a number of possible microstates. So, so when you talk about this absolute zero, you can only have, there's only one microstate, and that one microstate is when that entropy is exactly 0. And when that happens, so S equals to 0, because now this microstate is only 1. All right, so yeah, so that's what this third law of thermodynamics talks about. So the description is as such. Okay, so the third law allows us to assign an absolute entropy to each element and compound at any temperature. So, and at the same time, it also relates to this heat capacity, as you have seen before. So, and because according to third law, this S at 0 temperature is 0, so this boils, this is reduced to this, and so this is just Cp ln Tf, you know, over T initial, as we have covered in the previous lecture. So the heat capacity of a substance depends on temperature over a wide range. So if you're looking at this, for example, this is just an example that you can actually measure the entropy of a particular molecule in its various states, and just by taking into account the heat capacity at various phases, and that will add up to the entropy of that particular molecule or a system. Okay, and if so, you can also relate that when we actually do the PV diagram. Okay, the work done by plotting the PV diagram. So work is actually equals to the plot under the PV graph. So if you actually have this relationship, if you plot Cp over T versus T, so the entropy can actually be obtained from the area under the curve. So that's the relationship between that. Okay, one thing that you must also that I would also like to point out, that remember when we talk about this what they call enthalpy, the standard enthalpy, the standard state of enthalpy of formation. Now the standard state standard enthalpy of formation of an element is 0, and because it's not formed, and usually that it is in intrinsic state, so it's actually 0. But when you talk about the standard entropy for an element, it is not 0. There is a value because there is actually motion. It could be internal, external motion. So that internal motion, gives values to this element. All right. So entropy is a state function. So just how you actually calculate the enthalpy before this, okay, you have the total number of the products, total values of the products minus that of the reactant. So you do the same if you're given a reaction. So if you have a table values of the entropy for the products and the reactants, so you actually use the same equation, because entropy is also a state function. So here's an example that you can test out. So you're supposed to find the entropy change for each of the following reaction. So go over this for A, B, and C. So it's really very straightforward. As I said, this is a state function, so you just take the value of these product minus that of the reactant, and so you get the value. Of course, please remember to actually put the unit here, and the unit for entropy here is delta S, here is joules per mole per Kelvin. All right, right, so please do that. The units should be written there. Okay, now the next thing that we want to talk about is the Gibbs free energy, which is labeled G. Now, recalling what we have learned, so we have learned about this entropy change in the universe. And when we talk about this entropy change of the universe is composed of the system and surroundings. So because there are two different, two different entropies that you have to work on. One is the system, one is the surrounding. Okay, so it can be quite confusing, because at the same time you have to also deal with the signage. So now here's a look. Now we have seen this before, that delta S is equals to minus delta H over T. If you think about the reverse of if you have the system is actually minus that of the surrounding is minus that of the system, so this should be minus. So this originates from this equation, so the fact that it should be a minus here. Okay, so if you actually multiply the equation, this equation, okay, you have the universe times the system, times the surrounding and the system. Okay, so the system and the surrounding, the surrounding here, so then you have the T will be here, T will be here, so T will be cancelled because you have T in the as the denominator. So now, so what I'm doing here is the original equation is this, but I am actually making, so now you have to think about the system and surrounding. What if you just keep only one of the entropy? So let's just make the surrounding as the system. So if you do that, that should be minus of that. Okay, so that's why there should be a minus. So when I do that, okay, and I rearrange the equation, so I get this. So now I take, this equation. All right, so this becomes, just rearranging it, so you have minus T delta S universe equals to delta H system minus T delta S system. So in other words, I have changed, this equation from dealing with the entropy of the system to entropy of the surroundings. Now I'm just dealing with only the entropy of just the system. I'm only talking about the system. So that actually, simplify things. And this was actually proposed by, of course, the person who coined it J.W. Gibbs, and hence this is called the Gibbs free energy. So this term is what we call the G. All right. So the definition of G is equals to H minus Ts. So if you take the derivative of that, so you have this. Now in most chemical conditions, it's also always done at constant temperature and pressure, so that makes this 0. So now you can actually simplify that delta G is equals to delta H minus T delta S, as you have seen before in this equation 4. So this is just converted to delta G. So hence you have a new what do you call physical entity to actually describe, and this describe the spontaneity of a reaction, in which if delta G is less than 0, that means if it's a negative value, it signifies that the reaction or the change is spontaneous. If it's equals to 0, it is actually at equilibrium. And if it is larger than 0, it's a positive value, it's a non-spontaneous change. So this delta G describes the spontaneity, and at the same time it reduces the complexity of having to deal with the delta S of surroundings, delta S of the system. Now you're only looking at just one delta S, which is the system. Okay, that's the reason this Gibbs free energy is being introduced. So we can look at an example of the application of delta G. So the equilibrium temperature of water and its vapor, so you have here is as such. Now the delta H for the vaporization is 14.6 kilojoules per mole, and the delta S is as such. At what temperature will water boil spontaneously? Now given this delta G is equals to delta H minus T delta S, at equilibrium the delta G is going to be 0, so this will equate. So T, as you know, alright, will then be equals to delta H over delta S, and that gives you 373 Kelvin is the equilibrium change. Alright, 373, that's is also equivalent to 100 degrees Celsius. So at any temperature, so you know that that's the boiling point. So we know that at what temperature will water boil spontaneously? So at 373 Kelvin. So when it's above that, it's going to do that spontaneously, because delta G is going to be less than 0. Alright, so to summarize, this is the highlight, the key of today's lecture, that if delta G is negative, the forward reaction is spontaneous. If it's 0, the system is at equilibrium, and if it's positive, the reaction is spontaneous in the reverse direction. So these are the key points for today's lecture. Now this is another simple example. Okay, so you have here this reaction. So use the results of this calculation to determine the delta G for this reaction. Now you're given a set of values for delta H, and this should be delta S here. Okay, so all you have to do is find the delta H for this reaction first, and then you find the value for delta S, and using this equation you can actually resolve what delta G is. Okay, that's very straightforward. And because it's negative, so it's going to be a spontaneous reaction. So because so again you have this delta H delta S, which is a state function. It also, hence this delta G is also a state function. So that makes calculation on delta G very easy. So you use the same concept that you have the total number of products minus that of the reactants will give you the standard value of delta G. Okay, so this is example 4. Okay, use the data for the following reaction. Comment whether each reaction can occur spontaneously from graphite to diamond. And then, so the second question as well. So you'll find that the first one gives you 2.9 kilojoules per mole, not spontaneous, minus 183 kilojoules per mole for the second one. Now, based on this data given here, is spontaneous because it's negative. Now, A is interesting, especially the formation of graphite to diamond is not spontaneous. Now, I think on the first day of class, I did ask you this question. Okay, we talked about this. What if this, this graphite to diamond is a spontaneous reaction? What do you think is going to happen? Okay, so that's a rhetoric question, and so that's something that I want you to think about. Wouldn't it be, it will be really neat if it's a spontaneous reaction, but can you get around it? Does it mean that it's impossible? So again, it's a rhetoric question, something for you to think about, right? Okay, so that's it. Okay, so I'll see you in the next lecture. So this is just to motivate you to rise and shine in every morning, and just keep yourself motivated. All right, take care. Assalamualaikum warahmatullahi wabarakatuh.